Right now that Scott's not here, just answer all of his questions.
Yeah.
And he can watch the tape.
Okay, this is the quantum level, and this is the classical level. Right here. Now, let's first forget about product. Okay, so this is cochain complex over K bracket alpha, and this cochain complex over K. Right here. We know how to deal with this. First of all, the physical principle says that you choose a representative of cohomology here, you call it classical BV observable. Then you assign a representative of K cohomology class, which you call quantum observable. Right? So that is procedure. But that process is little ill-defined. But the thing is that you can, if you think a little bit carefully, you say that actually if you quantize different representative of classical observable, you should get quantum theoretically equivalent observable. And if there's obstruction during the concentration, it should depend only on the cohomology, or classical cohomology. So basically what I'm saying is that quantization should be sync, quantization observable should be thought as from the classical cohomology. 1H, this is classical cohomology. This classical cohomology, then we know there's a quasi-isomorphism between two. Unit-free-resolving quasi-isomorphism by choosing representative of cohomology class and extended linearly using John axiom of choice, etc. Doesn't need to be finite, but you always have cochain quasi-isomorphism which induce isomorphism on cohomology. So you can always do that. F. First let me call it that F. Now you want to lift this map. This map satisfied the F1H equal 1C and QF equal to 0, and the cohomology class of the cohomology class of image of this map is same as B. So induce isomorphism of cohomology like that. We want to extend this one to this cochain complex. We want to extend this map, and we call it F hat. Starting from F with adding quantum correction, etc. Now you want to this as a K bracket have a linear map, but you can easily change this thing. You got this trivial cochain complex of this guy here. So this is the classical limit, and this is the classical limit, and you want to let me draw a better diagram. We want to send C bracket alpha and CK. You want to change H bracket alpha, 1H, potentially 0. This is the classical limit of this guy, and this is classical limit of this guy, and you want to make a same map, which classical limit is F. You want to lift this quasi-isomorphism to this quasi-isomorphism. Of course, it is not always possible. Obviously not possible. But you know, classically, it is always possible. So the obstruction should be organized into a certain differential, kappa hat, which starts from ha-bar, kappa 1, kappa 2, etc. Okay, such that this morphism F hat, unit to unit, and should be commute with differential. This is a cochain map, and it should be cochain quasi-isomorphism as 4 my power 3, cochain complex over 4 my power 3. Okay, that's what you call quantization. and kappa is the obstruction.
So I think there's an alternative mathematical way to describe this. If you think of just the complex C with the differential Q, and then delta as another one-to-one operator that commutes with Q, right? Delta commutes with Q. So you have a one-to-one square zero operator that commutes with Q. So that's a that's a algebra over a certain operad, right? It's an algebra over an operad with just it has one extra differential on it. So when you look in homology, you get a model for that. You get that one differential. It's sort of infinity version when you go to homology. It's like a sequence of differentials, sequence of one-to-one operators, and I think that's kappa 1, kappa 2.
Yeah. So that is, but here, because what John is saying is essentially correct, but here the K doesn't need to have any restriction. It could be arbitrary quantum correction, and square to 0 and Q square equals 0. That is all the requirement we have, because that will be something we'll have instead of just having this right here. But that doesn't really pose any further mathematical challenge. It's the same thing. Other thing this really describing here is that you actually construct Hom complex here.
What do you mean Hom complex?
Space of Homs between H to C.
Okay.
Then you can form a Hom complex, right?
Yeah.
Space Hom, then Hom complex has natural composition. Like you can make it as a DG category, etc. Then you do the deformation theory of that thing over like K bracket Haber modulo Haber to N, etc. Like that to produce this one. Yeah. So you can say this is a kind of deformation quantization if you want to, in certain sense. But okay, all those things doesn't really matter. We can do this. And one way of doing this, there are many of doing this, is that, but it's essentially you are doing something very standard. So basically you have this quasi-isomorphism here, then you choose homotopy inverse and homotopy between them. Let me call it FH beta. So that is deformation retract. I call it on-shell to off-shell deformation, because this is where classical physics live actually, in the cohomology. Like here. Given this data, and you can produce, for each data, up to equivalence class, you can produce unique F and unique kappa, such that kappa square equals 0, and all those things, and this is quasi-isomorphism. Like here. Now, what happens if you change this data with different, like that, then there's actually there's a natural, on here there's natural automorphism. It's just linear differential operators starting from identity map with Haber, something like that. That thing, that you might go to here. Then actually they are all in the same orbit. You can prove that. So this is just an exercise of what you call homological perturbation theory, something like that.
Or, no, they call that homotopy transfer. You transfer delta to the homology, and you get kappa 1, kappa 2, kappa 3.
But you can do the entire
You need this FH beta to do the transfer.
So entire thing can be do that. Okay?
Yeah.
And I'll say that all those structures that I'm going to define, all those structures depends only on the equivalence class of this.
Yeah.
So you choose a quantization, and you know how to change to other quantization by some automorphism or something like that.
Okay.
You choose one, and you can find this kappa. So the important thing is that kappa now start from Haber. This is very important thing here. Now let me throw an algebra. The C. Let's forget about unit. But unit is important, but let's forget about unit. C dot and Q, and we add a product here, and then H. Then we have a uniquely defined product. We know that it's 0 here.
Yeah.
And then we have this F. What F will satisfy this guy? There, algebra homomorphism up to homotopy. Okay, and that homotopy is completely determined by this data too, essentially. So basically, homotopy is following. Like so you have a B. You define M2, B1, B2. This map, and you map by FV1 product FV2, etc. Then by definition, Qm equals 0. With 0. Then you use this guy, essentially saying that Fm. You're saying that M2, which is M2 is M2 is equal to, what is that? F M2H, composition M2H, plus Q beta N2, actually like that. So this is the, because
Yeah, something like that. Right.
so what is the identity? So which one is identity? Identity is F composition H is identity plus H composition F is identity on C plus Q beta Q. Essentially that's what I'm using. You just put in there. And this was this M2, what is M2? H is just the HM2. So this is M2. And we call it lambda 2 H. This lambda 2 is just beta M2. So you can choose this data, and then you have this relation, so this means that this F times F, right? So it's algebra homomorphism of the homotopy.
Yeah.
Right. So this is standard thing that we know. But now we have lifted this guy to C bracket Haber, the product in K, and there's H bracket Haber, and we have this kappa, right? Kappa starting like that. And we have this F here. So what did happen? What did happen is that, okay, F hat here. What did happen is, because of, they erase the relation, what is the name? The algebra homomorphism. So F B1 FV2 minus FM2 B1 B2 minus Q lambda 2 B1 B2. This is equal to 0. So if I change this to F hat and this guy to K lambda 2 B1 B2 plus minus lambda 2 kappa B1 B2 lambda 2 B1 kappa B2. Remember, kappa start from Haber. Okay, this in the classical limit vanishes. So this will be divisible by Haber. So let me define Haber pi 2 F B1 B2 in this way. Okay. Now if you, I'm only telling the very starter procedure. So if I get this picture, so this is definition of pi 2. I know phi 2 is a bilinear map. Find over there. Then if you make the computation, you compute Haber K pi 2 B1 B2 minus pi 2 kappa B1 B2. I mean, this will be the only computation I'm going to give. Kappa B2. You do this guy. You just this is home differential from here to there. You just apply that here, do the computation, and what you find is what this would be. That's actually F hat. So this is pi hat. f at b1, f at b2, bracket, plus f at kappa m to h b1 b2 minus m to h kappa b1 b2. Oh, this how about here minus m to h b1 kappa b2. This is just you just from here you just compute that, right? Because it's how about here because k x times y was if kx equals 0, yeah, kxy is the kx y plus xky plus half bracket xy. So you use that, you get this result. This is the consistent condition of that equation. But we know this is divisible by half because kappa is divisible by half. So define L to H defined by this guy. So we call this same entirely half L to H B1 B2. So this is definition. Thank you. Everything is divisible by half, so you divide everything. Okay, what you get is that you have K and bracket was DZA, but you have something like kappa and the homology and L2H, etc. And it looks like algebra homomorphism. Pi F1 is algebra homomorphism of these two real algebra up to homotopy, pi 2. So this you see the beginning of the ad infinity structure and homology, and the beginning of ad infinity morphism from the homology in this way.
Yeah, so you know, if you just look at C, forget H bar, just look at this complex C with delta and Q, then that's a BV algebra. You have a commute. So and then you look at homology. So one thing you can do is you can transfer delta and you get all these kappas. Another thing you can do is you can transfer the commutative algebra structure and you get like F2s and all these. You get the C infinity structure in homology.
Okay, so
and then you've got the bracket defined by delta. So you've got
kappa.
So you've got that Lie algebra, and you can sort of look at that in homology, or do some kind of BV transfer. And so,
okay,
do you have a sense for how different?
Let me answer the question. F hat has lots of beta in it.
Yeah.
H and beta with F. They're all.
Yeah.
This is already very crazy thing. Kappa is also constructed in that way.
Yeah.
Okay. Then this.
I feel like those two though are pretty easy to understand.
Yeah, it's like that. Then now, assume that you put explicit expression of this guy here in terms of homotopy transfer data. Okay. Then you try to find phi 2. This will be so complicated. So you can say this is the kind of master equation for all those relations that you will find if you do.
Right. I mean, I'm just wondering if there's.
But
see, if you have a sense for how different this is than if you transfer the BV infinity structure or something.
yeah, so the BV infinity structure is that basically. I can say many things about that, but the most important thing that is missing is weight.
Is weight the power of H bar?
Not really.
Could it be though?
Could it be? Yeah. If you think,
because you said delta has weight 1 and it has 1 H bar.
Delta has weight -1.
Or -1 because it's H bar delta.
Yeah. I mean, you see what the wave fitting. I mean, wave fitting does not really seems anyway. So we do this kind of procedure like here. Then of course for that we only did what for the product of two things, right? So this is not algebra homomorphism clearly, even of homotopy. You do the product of three things, product of four things, etc. Okay. Then you learn this machine that is kind of become a kind of combinatorial challenge, but you can clear that out, and then you can produce something.
So I mean, there's one thing is if you have a BV algebra, it's known, for example, that the brackets vanish in homology, right? And in fact, the whole L infinity structure is
Vanishes,
zero in homology. Because the bracket of two things is always exact because it's delta of their product to get started. But here, that's all just true up to h bar. So, so it's possible you're doing something different. I mean, it seems like there's something different here.
Because I never go to delta cohomology.
You never go to delta cohomology. Right. So, but at the same time, all you have is Q and delta to start with.
But we have much more. But anyway, Q and K, like.
I mean, the product. You have the product, and you have Q, and you have delta.
Okay, Q and delta, yeah.
So, so you're only starting with that material.
No, but the quantum mass, the action could itself depend on Haber. So that will produce all those higher terms as well.
The what? Say that again.
K was Haber delta plus bracketing with S hat something. But S hat has S plus Haber S1 to all those powers. Okay, so if I just write down, you can say this is Q plus Haber K1, Haber square K2, etc. It will go all the way. And the K1 contains delta, what is K1? K1 is delta plus the first of the power of this. This will be K1, etc. So we have that thing. But what I'm saying is that mathematically, there's no further difficulty than assuming this case. That's what I'm saying. So what you can say can be applied. But in general, we are doing this.
So with these higher homotopies, what is it that in the end you produce? So put in all
Absolutely, it doesn't matter.
So what's this final structure that you get? Is it like a map from H bracket H bar to C bracket H bar such that
this guy, so basically the thing is that if you compare the original BB bracket with this bracket, this L2, there's a differential and there's a associative product, commutative product here. So then what is L2? It's just the failure of caving derivation of that product. Like here. So this and it defined exactly the same way. Okay? But if you go back and forth, that will produce not just M2, M3, M4, etc. So, they become much more complicated. But in the end, what you produce is an L infinity algebra.
Where? On what?
On here.
On here, okay.
And L infinity quasi-isomorphism to this guy.
Yeah. So can keep answering Thomas's question like this. So you've got F hat. So F hat is F and a bunch of F1s, F2s, F3s, and then you've got kappas on H. So you make stuff on H and you make maps.
Yeah. So basically, we know that this guy contains C bracket Haber, K and the BB bracket, right? I didn't here, but from here by putting Haber bracket, like this, I have M2H, then we have a K and L2H, kappa and L2H that I just produced. But now if you go to the next level, you will get M3, which is not A infinity massive, but this kind of quantum correction of this guy, and produce together, combine this together, you produce L3H. So if you ignore n, you just produce an entire series. Then from F, I have F, you just say pi 1, but then I produce what is pi 2. Then you keep going, then you can produce pi 3, etc. Such that this is an L infinity algebra if you forget the product. And this was L infinity algebra, and there are L infinity quasi-isomorphism.
Okay,
Can
and
be
then what
viewed
about
in
the
this way.
products? The products are not C infinity structure in homology? Or
They-
A infinity structure in homology, they're not?
Because I told you, I'll let you use this symbol. M2H, M, not forget about it.
That really is the product in homology.
M4,
right?
this is really the product in homology. But you will have trilinear one with Gauss number -1. M4 -1. A whole series. Then you have M4 -2, M4 -3, the whole series. And this is the A infinity, minimal A infinity structure that we know.
Okay.
What I'm talking about here, I didn't go up to this part. This L infinity structure I'm talking about, this L infinity structure, is completely determined by this. So this does not yet appear.
Like the way the bracket is completely determined by delta,
And the product.
this L infinity structure is completely determined by these M's
Yeah.
and the kappa.
Yeah, exactly. So that like there's also quantum descendant and so on. So so this map, this quantization map, we made construct in that way, has that property. Somehow, if you measure the failure of F in algebra homomorphism of this descendant, etc., that will produce divisible by Haber, which is L infinity morphism, etc. So the quantization map has all the structure. So basically, so you only have product here, and only thing canonically we can define is the M2 here, M2H here. That is all you need. This is just starting process. You can go. You actually have to go like that.
This picture, like, should I think of it like a resolution of Gerstenhaber, like in one direction is the
Yeah, so
lead,
it's
and
that
the
is
other
it.
down
And then
goes
there's
the product
actually
or something?
Yeah.
kappa L2, L3, L4, etc. So this is all Gauss number 1 structure, and this is all Gauss number degree 0 structure, and this is degree -1 structure. So this is L infinity part, if you say Gerstenhaber, and this is A infinity part of Gerstenhaber, for example. Right. So, and it's also related to that. But
And then in Gersten, so I don't know Gerstenhaber infinity. So does it look like this, like a triangle? I mean, does it have these maps in between? I mean, must, right?
It has all of it, yeah, it's like,
It's more like a square.
I mean, you could think of this as a square, I'm sure, somehow.
By
this is
moving those
almost,
to the
yeah,
left?
Yeah,
Yeah.
what goes to the left. Okay, back and forth, and they are related very like this. For example, what does this relation tells you?
Wait, you're putting them in a triangle like this because
Easy to
it's
remember.
ghost number and weight. Is that
Also weight. This weight
I mean,
is
ghost number and weight?
This is the n-ary. How many n-ary?
3 to 1, 4
Yeah.
to 1, 5 to 1.
And then there's also the weight triangle.
So
There's
it's
a
like a pyramid.
designate. It's really like pyramid or something. And of course this has all formal power series expansion, right? This thing like that. So this like huge structure actually.
But yeah. But
But the thing is that they can be built from this. This
Yeah.
uniquely determined procedure. It will only depend on the equivalence class of this one.
So, but is there I mean, I don't expect you to say, well, this is an operad over, such and such a thing. But I guess I don't know how to ask, but I want to know, like, is there, you see, because you have something that's very much organized by H bar.
So
You pull out all the coefficients of H bar, and it looks like this,
at least in the classical limit, looks like.
Divide by all the H bars, pull out the coefficients, and then you get this these pyramid of operations or whatever, graded by Gauss number, H bar degree, weight. So how can you make sense of it?
So let me make sense of it. Try to make a geometrical sense of it. To make some sense of it, I can describe what is this morphism and what is structure and what is their relation they satisfy. Yeah. Now I have an entire list of relation, but oh my God, it's like usually I remember all those formula, but for this I don't remember.
Yeah.
So that is total mass, but it's a coherently defined thing. I know that is relevant for physics, but what it is like. One trick is that you just name it.
That's what I thought you were doing. Quantum QFT BV.
No, I could homotopy CQFT algebra and morphism of homotopy CQFT algebra and category of CQFT algebra. That is one way of saying it. Such that a two BV quantized quantum field theory has isomorphic correlation and homotopy correlation function if and only if they are quasi-isomorphic as homotopy homotopy CQFT algebra.
Right.
You can make that kind of statement, okay? But it's just a name. So let's put this.
No, but that makes it much better than a name to say that the correlation functions as defined, are the same if and only if.
Yeah. You can prove all those statements.
Sort of means the correlation functions are like the minimal structure of something.
Exactly. But the problem with the structure is that I can only define that as a generators and relations and collection of maps. Okay? In certain sense, that is not mass answer.
No.
Mathematics shouldn't be like that. Okay, there's part of mathematics, but mathematics should have a better name, better reason for that naming. So either it would be some kind of operad or quantized, or I don't know, whatever that's saying, they're coherently defined, so you can just explain what it is, and then you have sense of what it is, right? Instead of
is there something like, is there, you have, when you talk about operads, you talk about operads in different categories, right? Like in category of chain complexes or category of topological spaces. Is there a good, have you thought about whether there's a good category to talk about operads over, I don't know, over the punctured disk or something that have like this C, this K bracket H bar as their ground?
So perhaps I'm saying the remaining time I kind of a package. I try to describe package, and if you look up the package in the algebraic geometry way, it is like really you are considering some kind of topological structure, some object like bundles, vector bundles, super bundle, whatever, over the punctured disk, punctured formal disk, etc. And then you have some kind of Gauss-Manning connection with like Hodges theoretic structure, etc. That kind of thing will come up if you put in that way. And I like the structure because when I say this homotopy algebra, that is really about kind of a formal. If you expand all those structures in the formally, only in the formal neighborhood quantum neighborhood moduli space of given quantum field theory, you have the structure. But eventually we want to know the global structure, right? So then actually we better go to some geometrical category rather than stay in the pure algebraic category. So that's what I'm trying to do. Okay. So then I like to attempt that. What it is like that. So answer is basically all those operations that I wrote down all those, this product, all those things I wrote down is SL equivariant variantly flat
Because the product is
torsion-free formal.
Is that GL infinity? SL infinity?
L infinity, yeah. It's L infinity.
Oh, L
Yeah,
infinity.
because I'm always doing shifting, so let's take SL infinity. Just L infinity is it well?
Not like special linear, but like shifted L infinity. Okay.
Shifted L infinity is whatever.
Okay.
It's SL equivalent flat torsion-free formal Harbour sulfur connection. And the tangent, formal tangent to unclassical cohomology, for example, something like that. So that is the name, okay? But this name is much more coherent, so let me explain this name. And lots of things that you know we learn from topology will appear. So it's kind of a little bit fun, right? So begin with the axis, the basic setup, so background. That will be absolutely easy, background material. So B is we are doing finite dimensional case. As a free and finitely generated I module. And R is just a commutative, so this is a commutative K-algebra if you want. Unital or something like that. So eventually we will actually take either R is K or R is K bracket half. That will be in the end what you are doing. But here I'm considering half a completely out of vision. So B, let's start with B. It's a finite generated R module here, and it's graded, G graded. And graded by this Gauss number. Okay, let's consider this because it's pre and then it's consider a basis, choose a homogeneous basis, and then I choose a dual basis here, and then such that Gauss number of T alpha plus Gauss number of E alpha would be 0. It's dual, like here, and then make it supersymmetric. So T alpha times T beta equal to -1 of Gauss number of T alpha, which I denote alpha, and Gauss number of beta, and T beta, T alpha. We define this product structure, then you consider K formal power series in T. T equals TB, and equal to TB because I don't need then everything. So consider with this product, then this is algebra. This is K bracket, then this is isomorphic to the completed symmetric algebra of dual of B star. And you make it as a half. Yeah, we don't have half. So this is isomorphic to that. So you can say this is. Now consider M. M is the kind of formal spectrum of this thing. So kind of affine space over R. So M is like a formal spectrum of this guy.
So that thing is like the ring of functions on that.
Yeah, that's so essentially okay. I regard that as just same module of some affine version of affinized version of module. Essentially, you have this guy here. Then you also consider d alpha. D alpha is the dt alpha d. Okay. Now you can extend this as a linear derivation on this space. Okay, like that. Now what you do now is that now I want to define differential form on this space. So I want to define space of formal differential form on N. And there's a standard algebraic construction that you can do, but essentially this, I would say, this is isomorphic to K bracket alpha TV and theta B. What is theta B? Theta B is the formal symbol. For each T alpha, you formally observe dt. So this dt, theta alpha, like here. So it's theta alpha is just dt, like here. And you make a pre-module out of it. Module generated by this symbol. And then go to some kind of exterior algebra, etc. But here, let me introduce another degree. So we have a Gauss number. We have Gauss number. So the Gauss number of T alpha is T alpha. And let me introduce form degree of T alpha. And say this is 0. Okay. Let me call this form degree of theta alpha is 1. And the Gauss number of theta alpha equal to Gauss number of T alpha. So you keep the same Gauss number, but you introduce grading, form degree, so theta alpha is 1, basically. Then denote by this guy, x is the Gauss number of x plus form degree of x. So this is total degree. Thank you. Total degree. Then you make this algebra, and where this generating relation, now we can say is the T alpha T beta equal to minus 1 of T beta T alpha, and T beta theta beta equal to minus 1 of T alpha theta beta and theta beta T. I'm writing this down. Theta alpha theta beta equal minus 1. Total degree theta beta theta alpha. So basically, you know that total degree of theta is always 1 larger than total degree of T. So basically what you are doing, this guy is isomorphic to symmetric power of B star cancelled with the symmetric power of B star shift by 1. Okay, so this algebra, let me call this differential form, algebraic differential form over here. Then you have exterior derivative d, which is theta alpha. I'm using Einstein convention, dt alpha d. You just extend this as a linear derivation, etc. Then this summed over, then d squared equals to 7. And d is the derivation of multiplication, etc. So we have a omega 0 and times d and the product. So this is the algebra of differential form on N.
Yeah.
Okay? This is it's a graded. This is graded spec. Okay. So it's just the algebraic differential form you construct here. Now assume that B is an SL infinity algebra over R. Assume that over R. B is also SL infinity algebra. So meaning that, of course, we have this bunch of operation L1, L2, L3, etc. From what is that? This Ln is from symmetric power of R of B to B, but the Gauss number of Ln equal to all 1 and satisfying the same relation as L infinity algebra. Okay, but this is equivalent to derivation of omega 0m. This is bullet. Omega 0m, which is isomorphic to k bracket t. This thing, TB. A derivation of this guy with form degree delta, a derivation delta of this guy with form degree delta is 0, and the Gauss number of delta is 1, satisfying delta square equal to 0. So it's just that. That's an SL infinity structure on B. So it's just a derivative. So if you want, you can write down in this way. Delta, you can write down the sum, and because we have a n equal 1 to infinity, m factor over 1, t alpha n times t alpha n, something like structure constant L alpha 1 alpha n gamma delta dt gamma d. It has this kind of expansion if you use, because t alpha is like coordinate. This is just affines. This is just, this is just flat structures, flat space. So this is coordinate, and this like vector field which is square to 0.
Yeah. An arbitrary derivation looks like something times dt.
Exactly. But now you just fix the Gauss number and the form degree. Form degree also automatically delta square equals 0. That would be on L infinity 0.
What are the L's? Are these numbers? Or
You can L. What is
It's not
L?
the same as
Alpha
those
1,
numbers.
alpha n gamma. E gamma is a structure constant. So in alpha 1, E alpha n. So this all belong to R.
These are those LMs.
Yeah, these are those L. So we can
You
move
have
back and
those
forth.
maps, then you take their coefficients, and you get a whole bunch of numbers, and you can make that power series. And then you did not write down what it means for delta squared to be 0, but you
Yeah.
can imagine.
You can imagine what it is. Okay, here. And then there's exist a unique extension of delta to what I call delta tilde on omega bullet m, not just as a this was only acting on t, right? But now we have theta part, differential form part. You can extend this one as a derivation with same degree, etc., which commute with d. So d delta tilde plus delta tilde d equals 0, and delta tilde square equals 0. There's a unique extension of that. What is that saying? Delta tilde, I can write down delta tilde, it's very easy. This is just the summation, and it's 1 to infinity of m factor over 1, just theta beta and t alpha n L alpha 1 alpha n beta gamma d theta gamma d. This is delta. Delta is this, delta minus this would do that. So there's a unique extension, just as it's square to 0. Now it involves kill theta term, but it also commute with exterior derivative.
But what mathematically, what did you just do? Can you explain? Delta is a derivation
On 0 forms.
on 0 forms, and uniquely extended
To a derivation on the entire form, such that
on the functions it gives you.
delta, original one, but it also commute with exterior derivative.
Okay.
There's such a unique extension there. Yeah. So we have this chain complex with M with D plus delta tilde, which is squared to 0, and we have this product on here. Okay, we get this guy here. And what is this? We can name this as this is SL equivariant bimodal of bimodal of SL equivariant cohomology.
Well, now you're making me think. You have a derivation of the functions that's like a vector field, right?
Bimodal of SL infinity equivariant cohomology. Okay. That's analog of that thing.
Well, wait 1 second. So you have this L infinity algebra, but you're viewing it as a derivation of the functions on something. So it's a vector field. And then somehow it acts on the forms. Or you can.
And this is squared to 0, so that you can form a cohomology.
Probably by interior, right? Because you have DD.
So
Theta I, so you do the interior on a theta I. Like,
so this like
That's what d by d theta I.
this is the interior theta I. Okay, that's what you're doing. So how why this? But this is kind of interesting because I don't want to just throw names. So let me say why this is why this is the correct version, or whatever it is of this one here. So let me assume that B is B0 and B minus 1. Degree concentrate 0 and -1.
Yeah.
Okay. Then let me choose a basis here, EA, EI, and let me choose basis here, EA, whatever it is. So this is a basis of E alpha. Then you have T alpha version here. Let me call it TI, and this guy eta A.
Okay.
This goes number 0 here now. This goes number 1, because this is 0 minus 1 here. Then we have BT, theta alpha, and we call it, this is essentially DT. This is CI, and we call it pi A. And this guy, because shift by 1, the total degree is 1, this is total degree 2. We have this guy here. And so what is our D? D was very simple. Pi dti d is del d eta A d pi A. This is our D. Okay, what is our delta? By degree reason, there's only thing you can write down is actually eta A eta A ti ri aij dti jd plus 1/2 eta A eta B fa dc d eta c d. This is all you can write down here. And this is an element in module. The ring R, so they are the coefficient. Okay. Now what this means, what delta square equals 0 means, following. It means that B minus 1 It's a Lie algebra, structure constant of this guy. And it means that also B minus 1 act on B0 by linear representation. This is matrix. Okay, so that the scale is 0. So actually Lie algebra acting on a space. Lie algebra over R acting on the R module. So you're making Lie algebra module of this. So this is delta that you can uniquely write down here.
So you should think you have a group acting on a space.
Yeah.
So then you look at the forms.
Yeah.
Wait.
Group acting on the state, then you are actually building onto equivalent cohomology by going this Borel construction. Then you construct the drum model of it. Okay. There are two drum models. One is Cartan model, another is Weil model. Okay. Cartan model kind of take tensor product with your differential forms with the symmetric power of this even element, and you deform your exterior derivative by interior modification of this vector field acting on an action. Okay, then that deformation will scale to not zero, but it will be derivative. So if you consider G invariant part of that thing, you have a cochain complex, and the cohomology of that thing is the G equivalent cohomology. That is Cartan model, and the Weil model is little different. It is Weil differential is actually scaled to that form. So you can say this d G at infinity is defined to be d plus delta tilde. And then now you can build up what is delta tilde, what is d tilde. You can easily do that. dg infinity. What is this guy? Instead following the law, that is exactly the G equivalent cohomology. The V minus 1 acting on this, and this cohomology, this is exactly the G equivalent cohomology of V1, drum cohomology, etc. Or you can build a case, another interesting case, which I like very much, is that now you have a V1 part here. Okay. Then what you're doing is that you have the space, you have group acting on it, on the space, the B is the algebra acting on here, but V1 part is the fiber of some vector bundle, group is also acting on here, and then there's equivariant section between here to the map there, which is equivariant, etc. Then you construct model for that. Then you want to compute the equivalent cohomology of vanishing loci of section divide quotient by group G, what will be the cohomology? And then model compute that thing, which appear in the always used by Ed Witten to make topological quantum field theory. That is Massa equivalent form superconduction set. Drum representative of Tom class you can also get this way. Okay, so this is all of this whole generation here. So it's very simple gadget, but it has many those constructions. So this was the example. So it's, you can simply say this is Weil model of SL infinity cohomology, equivalent cohomology here.
Do you have any sense if you add one more of V2, what you get?
Yeah, but that is actually very interesting, but yeah.
Well, what?
What you get?
The section I described, equivalent, is always quadratic section. But now do we have this high order sections as well? So in certain sense, that computation would lead some smart person with knowing enough would build up the kind of equivalent Tom class for some kind of global version of L infinity algebra is acting on it. And you do the entire Chern-Bell theory. Equivalent version of that kind of thing may be doable.
You know, when you have a group acting, right, infinitesimally you get a Lie algebra acting.
Yeah.
What's the...
I don't know.
What? Okay.
So that is I was not, okay.
No, but it's somehow in,
Yeah.
in this story.
In the story. But if somebody can tell me, I would be very happy, but no intention by myself to investigate that thing. But anyway, that kind of structure, this very simple guy, that kind of construct huge structure, right? That's what I'm saying. Now, this is not my point. The point is now we want to go to the equivariant superconnection. So you go to the tangent bundle to M, which could be also algebraically constructed. Okay, but this is trivial. So tangent bundle, this is really just isomorphic to M times B. We start with trivial one. We could have started non-trivial one as well. So we can regard this d alpha, which is dt alpha d. This is a plane field of this tangent bundle.
Dude, that's just like putting the E alphas back in.
Yeah, it's like E alpha is back in exactly. Yeah. But yeah, like plane field around here. Then we consider omega bullet MTM. It's a tangent bundle valued differential form, which is, of course, this is like tensor product with omega 0 by then, which is with the section of this guy. Okay, let's consider this here. Then superconnection.
Wait, is that one? Those are just, they're not polyvector fields, they're just vector fields.
Yeah, this is just the
Or
tangent bundle, section of tangent. Yeah, not fully vector field. Interesting. SL infinity equivalent superconnection. On TM, it's just the delta like G infinity. It's a homomorphism from omega 0 to bullet. Let extend MTM to omega bullet MTM, right? But now we
wait, you don't need to put a vector field in also at the beginning?
What vector field?
Just think of a connection as you put in a vector field and
but you can regard this as just a linear map from space of section to the one-point valued section with certain property. That is same, right?
I think that dot is encoding all the degrees, maybe.
And then also, but we know that this M was graded, but V was graded by Gauss number and form degree. So this kind of thing is all bigraded. So this is saying the form degree, but the total degree of this thing is 1. So it could be 0 form and Gauss number 1, or 1 form and Gauss number 0, etc. So it starts from 0 form and to all not just the degree, yeah, like that, such that delta G infinity of some function from section or omega equal to this minus, how do you call it? Yeah. Minus 1 of total degree of omega and omega delta G infinity dot S is equal to D plus delta acting on omega tensor S. Okay. So this is the definition of superconnection.
so you have a D plus a delta.
Yeah, I have D plus delta. Yeah. So this is C equivalent superconnection around here. And our standard is that all connection. This is kind of life in all connection business is that if you choose another superconnection, the difference would be endomorphism, right? Because this will be all same, right? So it means that delta, and we know that also D plus delta is superconnection. So any delta G can be written as a D plus delta tilde plus some B. B is the endomorphism of tangent bundle. Form degree plus Gauss number equal to 1. Right here. So B can be decomposed as L plus A. This has a form degree L equal to 0 and Gauss number L equal 1. And this is form degree A is larger than 1, etc. And Gauss number like that. You can decompose in this way.
I'm sorry, what is B?
B is the endomorphism.
The connection, you're
Yeah.
thinking of like
Connection
D
form.
plus a matrix or
Yeah,
something.
D plus matrix. But now this guy has a zero form and Gauss number 1 part, and the M forms with Gauss number 1 minus M. So it'll have A has A1, A2, A3, or etc. Okay. And this connection is flat if delta square G equals 0. This is flat. So you say this is definition of flat. Equivariant flat connection.
And it's equivariant with respect to little delta, right?
Yeah.
I mean, that's built into
Yeah,
it.
built in. So it's like that's what yeah.
So how do you know such a thing exists?
How do I know such a thing exists?
Right.
I just constructed. This is one example. This was superconnection.
Zero
When
is
B
one.
is 0 was superconnection.
Oh, I see.
And B is just arbitrary, just endomorphism valued bunch of things satisfying square to 0. Right? And this is like this nice linear space, and so absolutely no problem. We have no topological problem. We can just do that. Of course, there will be version of this in the changing M to really super manifold or something. And then that will be quite interesting. Anyway, so finish it. It's time up here. But
Okay, and then where are you going to put H bar?
okay, now let me start with H bar. Yeah. What I'm going to separate H bar. So now instead of B, we are considering H and H bracket Haber. This the classical thing here. Then you know there's a Gauss number and there's also weight. It turns out, as I said, when I make this ad infinity morphism, homotopy, quantum random variable, etc. So I did like T alpha, pi 1, E alpha, etc. They call it gamma. Then I divide by Haber and put E2. Define like this. So I'm going to make this gamma as a deformation of action. To do that, I have to always choose gamma to be weight 1. To do that, the weight of T alpha should be 1 larger than E alpha. Okay, if you do that business here, then it turns out D has a weight -1, or D. So instead of D, I'm considering Haber delta, Haber D. So D has weight -1. And all those delta and delta tilde I construct would have a weight 0. And all those super connection, I'm going to construct here B would have a weight 0. Okay. So I'm putting Haber here.
That's it.
That's it.
And B has lots of H bars.
B has lots of H bar, but now I need to also condition that L has Haber, but A does not depend on Haber. Okay. N is scaled to 0. Then I call it equivalently flat H bar connection. H bar super connection.
And so since we're basically out of time,
Yeah.
I mean, so all of those F hats well, maybe not the F hats.
No,
but the,
M's
with the
and
M's
L's.
and the phi, not the F's and the phi's, but the M's and the L's.
Yeah.
And all their H bar components and everything you can put together into.
Then you do the expansion. This we are doing formal superconnection over this formal power series ring.
Yeah.
You expand this, and they have the degree relation, they have the Gauss number relation, there's form degree relation, and the weight relation. You can expand this coefficient, then you have infinite by infinite multilinear maps on the same. And satisfying relation is really just the delta G square equal to 0.
Okay.
No, that is.
And vice versa. Every one of these.
And
is
vice
one of
versa.
those.
Yeah. So, but this, because putting Haba here, you will get this. This is not really connection, right? When you define connection, that delta commutator of function should be D.
Yeah.
D omega. But you put Haba here. Okay? So this kind of connection was first, it turns out first considered by Batalin and call it lambda connection.
Yeah.
And related some kind of a some Hodge theory, because it's Tanakian category business or something like that. It's naturally appeared there. So Haba played that role. Okay. Now we have the super connection, and so there will be
You
some
can kind of divide by lambda.
no.
To put lambda, sort of have like a
Batalin-
1 over lambda in front of.
Yeah, but the Batalin interpretation is this. So, here. And we are doing, but you have a meaning. What is this lambda? This could be regarded as some map from disk to affine space, etc. Right. So some geometrical meaning. So that the formal disk or formal whatever that I feel. Okay. So this was formal algebra, entire algebra structure here. Now, of course, this condition squared zero. We are very clear. This squared zero condition of this one up to this one. One example would be, what would be that one example? That should be Haba dB plus B square equal to what? Delta tilde B. This would be like Platon's equation, right? Equivalent flat condition that you will have. You see all those things. Like this is what just generalized connection, and this is just a twisting chain that you'll feel there. Thank you. Now, to include the morphism, you have to take this H.
Now you're going to tell us what the F and the phi's are.
Yeah. Then you take the H and the TH. Okay. And you tensor with C. And you take the bracket Haba, you consider this, you can do that. Then you have this delta G here. So you have Haba D plus delta plus B, etc. This part, from here you get K. And delta actually contain, delta start from kappa, then kappa, etc. You have this guy here. Then natural twisting cochain you can write down in this situation. This is square zero thing, homotopy, whatever. Flat, so this is differential here, and there's a square zero differential here. You're taking tensor product, so on, then you can form a twisting cochain.
And the mixing parts are the
Missing parts of them, like all degrees, okay? That twisting cochain, now you has a, with particular weight and degree, etc. You expand that all those things in the formal power series, then that make F, phi 1, and also then you just not have phi 1, which was F, phi 2, phi 3, etc. But you'll have a phi 2 minus 1, phi 3 minus 1, phi 3 minus 2, all those sequences. That this is actually adding A infinity quasi-isomorphism. And this guy is the L infinity quasi-isomorphism of those descendant, and that is all those things combined in this twisting chain. with the lambda connection. So that is the answer. So if you do the finite dimensional here. So somehow it has a lot to think about. This structure has a lot to think about.
Yeah.
Because like that it maybe eventually tells you that what is the algebra is, what is the interpretation there, and perhaps you do have to some formal algebraic geometry, etc. Then you do all this.
But is there a sense in which this this picture of, so C is like the space of quantum fields,
Yeah.
H is like this universal parameter space, you know, and functions on fields, and so you're parametrizing, or I don't know, is there something physical about this picture?
Yeah, so the physical about this picture, that's physical about this picture. This basically, you are dealing with the local model, formal neighborhood of your modularized space of quantum field theory. It has some modularized space component theory has this geometrical structure. But you look at the formal neighborhood of your modularized space where your original DB is started. If you look at expansion, like formal neighborhood has this structure. So this H, what is H, is just essentially tangent pointer of this modularized space that like, at the base point. So that's why we have a formal surface connection on here. And there we have a tensor product structure. There's not really many crazy non-trivial things appear because everything bundle we constructed is trivial bundle, etc. But that is just a local trivialization. So quantum field theory is nearly say that you have some huge geometrical structure that understanding that and just moving around that, this is you have flat connections, you're kind of you're moving to the formal neighborhood. You're kind of moving around the space and how your theory changes, like how is things transferred, etc. Then somehow generate quantum correlation function, generating function of entire quantum correlation function is kind of section.
Yeah.
Some kind of equivalent section over here, but now you do the integral. You apply C hat to this structure here, then this part will go away, become number, okay? Then you will get this purely geometrical thing. That is the kind of quantum crystal or something like that. That has this structure. So that is kind of something this picture is saying. And, you know? So I'm not completely satisfied because this is purely formal neighborhood picture. But at least, okay, we know how formal neighborhood of quantum field should look like. Yeah. Then the claim is that this is entire information of quantum field, except your singleton.
Okay.
It's about singleton. And we can use this structure to return back what was quantization. Right? Then I can give much coherent answer. Then if you give me the classical action, how can I get S? K out of it, and how can I get this one? Can be all streamlined to have a coherent description, etc. So I think the end result is actually more interesting than how I get it. Because
So in your equivalent superconnection, do you assume your tangent bundle is trivial, or?
in this case, it's trivial. But
There's
absolutely
really.
absolutely no reason to be restricted to the trivial. I mean,
Right,
that's
right.
like, you know,
Yeah, I see.
there's absolutely this construction can be done here. So basically,
Wait,
formal
that-
neighborhood. So we actually want to understand this modularized space map as some kind of, I don't know, maybe some formal, some stack or infinite stack. I don't know. It's like there will be some nice geometry and topology here. But I do not know what it is because I'm just a formal guy. And because my goal is to understand correlation function of quantum field theory, it essentially tells you that what is your formal neighborhood looks like in this like that. So if it is then around here I can do the trivialize with H. It's a fiber. Like here, there the structure I constructed. But then as the entire structure should be constructed here. then we will have all those monodromy construction. Where would be singularity, degeneracy, all those things. That kind of should be done. And after doing that, that would be really the quantum field theory.
Right.
Yeah. So we are heading to the. It tells you that clearly what it should be quantum field theory. So now we have to. Yeah.
It's like
this
the
was
moduli
exercise.
space of genus G curves or something, and you're just telling us the dimension.
Yeah. Something like that. And some of formal structure I can get out of it. So that is the construction you should give down here.
Okay,
And
wait, let me stop you and thank you officially. If there are any more questions, I'm going to run out, but if there are any more questions.
Next I have is,
Now coming to, do you have Jung's number?
Do I have beyond this?
Well, I didn't bring my cell phone, so